let's see how a MOSFET behaves or acts at a kind of a more detailed level. So far, I mean, we looked at it and said, well, you know, if the VDS is small, you know, this is the surface, this is the channel charge, and then you can calculate the current based on that. And we saw that for small VDS, the current was proportional to VDS, and the proportionality was also controlled by VGS. But now let's look at this device, this MOSFET device, more carefully. So let's look at this. So let's say we have an NMOS, and then we have the gate oxide insulator, and the conductor here, which is the gate itself. So you have applied VGS here. This is the source, grounded, and this is VDS. Now, so let's say initially, when we had very small VDS, or VDS was 0, and we had a VGS above ET, the threshold voltage, we had this electronic charge at the surface, right? So we had this layer of charge, inversion charge, that can carry current for you from left to right or right to left. But now, just, so let's say we apply a larger VDS. What happens? Well, as VDS gets larger, and it's not close to 0 anymore, what happens is that the voltage drop across this side of the gate, between the gate and the channel, is smaller than the voltage drop between here and there, right? Because you're raising the channel voltage here. By applying a larger voltage to the drain, you're increasing this voltage, and therefore the difference between these two becomes smaller. And hence, it shouldn't be too surprising if I tell you that the density of the surface charge is smaller on this side than this side. So you have more electrons here than there. But you can also see from the energy band diagram, because this side is kind of now going down, so you basically see that you have fewer electrons here. Now, the way we show it symbolically is by showing this inversion layer charge as a kind of something like that, and thinner on that side and thicker on this side. So this is to imply that the density of free electrons here is greater than the density of free electrons there. Right? What is the density of free electrons at some point? So let's say surface inversion layer charge at some, let's say, point here. How do I calculate that? Well, let's say that's this point x on this axis. So let's call this V of x. If I know the channel voltage at that point, can you tell me what is the surface charge density for that point? What is Q per unit area at x? Well, think about this. If my source were, instead of being whatever, this is my new source, right? This is like a little source here. So the voltage difference between these two, whatever voltage difference you have, in excess of Vt, that determines my excess charge, right? Inversion charge at that point. If you look at it locally, it's like a little transistor. So you have a voltage here, you have a voltage there. This difference is my VGS for that point. And whatever excess voltage I have on top of my Vt, that should good. So that would be Cox VGS minus V of x minus Vt. So this is this voltage difference, because this voltage is constant. This is a conductor, right? It's constant all across. Minus Vt. Okay? So that's my charge density there. So now, if I were to break this transistor into little slices, so they are sliced in this direction, so this is the third dimension, right? So let's say I have a little tiny transistor here. Think of it as, let's call this dx. So the channel length of this tiny transistor is dx. Its channel width is the same as this transistor's w, right? So all the same across. So I have a tiny transistor there with a channel length dx and width w. Within that transistor, I can still assume that the electric field is constant, right? If it's an infinitesimal transistor, it's a good assumption. And I can use that model, basically. So what is the dq? W times dx. So it's W Cox VGS minus V of x minus Vt dx. That's the charge. Now, I need to calculate one more thing to calculate the current, d tau. I need to calculate the time it takes for an electron, average time it takes an electron to get from this edge of this tiny transistor to the other edge. Now, for that, I can assume the electric field is constant across this thing. Because it's such a small transistor anyway, it's an infinitesimal thing. So, I can calculate it the same way. I can say, well, it's really L, the length divided by the velocity, so which is, the length is dx, divided by the velocity, which is Vd, the drift velocity. Which is what? Dx divided by mu e. Right? Really, this is Ex, because there's Ey too, but we don't worry about that. So you know that it's E along the x direction. So this is mu n. Ex. But what is Ex? What is E? If I assume it's constant, I know E times this length, dx, is going to be the voltage drop across this thing. Right? It's dV. So I can write this dx, this mu n, as times dV divided by dx. Right? dV dx, basically, is the slope of the potential with the electric field. It's a minus sign. Forget about that now. It's absolute values, right? So I can rewrite this as dx squared over mu n dV. But the current, what can I say about the current? Total current in this transistor has to be the same at any point, because all of these transistors are in series, right? So I have another one next to it, another one next to it, another one next to it, and there will be a constant current ID flowing along all these. So ID is simply dq, so it has to be the same for this guy, this particular guy too. It's dq to d tau, by definition. Okay? Now, so let's calculate that. It's W Cox VGS minus V of x minus Vt dx divided by the d tau, which is dx squared divided by mu n dV. So one of these guys cancels that, and I'm left with what? Mu n Cox W VGS minus V of x minus Vt times dV divided by dx. Okay? Agree? Okay. So what I want to calculate really is the current in the transistor in terms of the voltage drop across the whole transistor, the big transistor, which consists of an infinite number of this infinitesimal transistors in series. So what I really want to calculate, so I can rewrite this as ID is dx times dx is mu n Cox W VGS minus V of x minus Vt dV. So I need to integrate it from this side to that side, right? So I integrate it from this side to that side. I say integrate it from 0 to L across the whole transistor. And I need to integrate this from 0 to what? If this is at 0 volts, I have to get this voltage on the other side, right? Which is what? VDS. So I know this is constant across the transistor. If it's rectangular, I mean, the density has to be constant. So this is the same. So basically this becomes integral of dx, which becomes L. Right? So this side is simply ID times L. And this side, these are all constants except for these. So it becomes mu n Cox W integral of this thing. Now what is the integral of this thing? It's this thing minus this thing squared divided by 2. Evaluated from 0 to VDS. Let's do that. So it's minus that thing, that argument, squared over 2, evaluated from 0 to VDS. So what is it for VDS? Let's plug it in. So it's for 0, let's just do that. So it becomes mu n Cox W. You get minus VGS minus VDS minus VT squared minus Vt times V of x, and then that part gives me a V of x squared over 2 from 0 to VDS, right? And I evaluate that, and simply it becomes, and I get the L on this side, so IB becomes VGS minus VT times VDS minus VDS squared over 2. Right? So what I have is an expression that relates the collector, the drain current, to the gate source voltage, the gate voltage that controls the resistance, and to the drain source voltage. Now you can see for small VDSs, this term is not dominant, it's going to be small. So it goes back, it reduces to the expression we derived, so it becomes linear. Right? We have that relationship. It reduces to that. But now, if VDS is large, then there's a second order term, a correction term that makes it nonlinear. So the relationship is not exactly linear anymore. It basically becomes a limiting term. So if you look at IB versus VDS, for small VDSs, of course for different VGSs you have different lines, but it's kind of a linear behavior. But then it starts going down. It doesn't grow as fast without the second term, which is a minus sign, so it kind of limits it. Okay? And this is the behavior, this is the expression we will use for what we call a triode region. For the MOSFET operation. Okay? So that's the expression. So we derived it, and this is, you can see, it came from the fact that we basically assumed that it consists of infinitesimal transistors. Okay? Any questions about this? No? Alright, good. So, that's a triode region. But now, for this to hold, of course we have to have a certain condition to be met. So let's look at that, look at what conditions we need to have for this to hold. Now, what happens if I keep increasing my VDS? Right? So let's look at some, let's look at the charge density, the inversion charge density right next to the drain in the channel. Right there. Right next to the drain. As I increase VDS. So let's see, what is that density anyway? In terms of the voltage that I have. Can you tell me what it is? Well, this expression was general, right? So we can evaluate this expression for Vx equal to what? At this point, what is Vx? VDS, right? Exactly. So the charge density at that point is simply Cox VGS minus VT minus VDS. Well, yeah, that's the surface charge density, the inversion charge density. So what happens if my VDS is equal to VGS minus VT? If my VGS minus VT is equal to VDS, what happens? There's no inversion charge, right? So that's what we call the pinch off. The channel is pinched off at that point and beyond that point. But does that mean that we have to carry no current? No, right? It means the density of charge is 0 here. But the charges are flowing, I mean the electrons are going this way anyway, right? And there's nothing to stop them. The same way in the base, you remember when we did this exercise, when in the base of the transistor, on the emitter, on the collector side, we said that on the collector side, because everything that gets to the edge of the depletion region on the collector side is sucked in, the density is 0, because nothing can stay there, right, in steady state. But it doesn't mean there's not a flow of charge, there's a huge flow of charge. But it means that there's no net density associated with that point. Okay, so that's where we get to pinch off. Now, what happens if I go below, above that? If VDS goes above that, what happens? Well, not only at this point, but also at some point beyond it, I will have no surface charge density. So again, symbolically, I can show this new channel like this. So this is this inversion charge, and I don't show anything here. Now, let me ask you an interesting question. I mean, it's a relatively simple question to answer, but just what is Vx at this point, at the edge? Right. This voltage had to be equal to VGS at that point. If that voltage is VGS, this becomes 0. That's the verge of where it becomes 0. So this point, the voltage at this point is always VGS minus VT. Okay? And that's something good to remember. So the voltage of this point is fixed, no matter what voltage you apply here. What happens if you apply a larger voltage here, this point goes farther out, farther to the left. If you lower this voltage, it comes back here. For as long as you are in the pinch-off region, you have this pinched-off channel. Basically, for as long as VDS is greater than VGS minus VT, which is a condition for pinch-off, this voltage is fixed. So now, what that tells you is that the condition for this thing to hold is that VGS minus VT has to be greater than VDS. So VDS has to be small. So this trial operation holds when VGS minus VT is greater than VDS, or VDS is smaller than VGS minus VT. But now, beyond that, what I can tell you is that VGS minus VT is fixed. Now, even if I apply a very large VDS, what happens is that this goes a little bit farther out. Okay, changes a little bit, and most of the electric field actually falls across here. This is the interesting thing to remember about MOSFET. Because in a lot of analog design, when we will be dealing with this pinch-off region, this region of operation. And what happens is that, although you have a relatively large channel in this case, most of the electric field you apply to the VDS, most of the voltage you apply to the VDS drops across this small region. Now, in the energy band diagram picture, what that corresponds to is something like this. So you see, when we were in the triad region, we said, well, we've lowered the potential barrier, so it kind of looks like that. And then this is the EF and EI kind of remain below that all the time. Now, what I've done here is I apply a larger and larger voltage to VDS. Initially, when I applied the small drain voltage, I just tilted this a little bit and the charge flowed, right? So the flow of charge was pretty much limited by what? By the resistance of this channel, by how much it's tilted and what the mobility is and all that. Right? We even could calculate the resistance. So we have something like this. The energy band diagram, the conduction band and valence band look like that. Right? When I apply a small VDS. Now, if I apply a large VDS, so this channel, this part is what controls the flow of how much current will flow. Right? Now, if I apply a large voltage, we saw that beyond a certain point we have pinch-off, and most of the electric field will fall across. So this is the pinched-off region. Right? And of course, any electron that makes it here will go down the slope. That's not a problem. But let me ask you this question. So, which one of these two regions do you think controls how much current flows? This region, the pinch-off region, or the channel? The channel, right? That's correct. Why? Because that's the bottleneck, pretty much, right? I mean, it's like having a very thin pipe attached to a huge pipe. Right? This region is capable of carrying a lot of current. It has a large slope. Right? But it can only carry all the charges that's supplied to it. So this is a thin pipe, followed by a very thick pipe. And this is your source. So it doesn't matter, right, how big this is. The flow is limited here. Now, that tells me what I can how to derive an expression for the current in the pinch-off region. Well, to the first order, if I know that my channel length is not going to change much, right? The voltage across the channel is fixed, right? What is the voltage across the channel? Look at that picture. Look at that purple script on it. It's just VGS minus VT, right? So I have a fixed channel which doesn't change that much in length. and its voltage across it is VGS minus VT. Therefore, is it fair to say that my current would be what I get for a VDS, which is equal to VGS minus VT, the first order, in the pinch-off region? So I just need to plug VGS minus VT as VDS into that expression. And when I do that, I get something like this. So in the pinch-off region, interestingly enough, according to the simplified model, my current is going to depend only on VGS to the first order, based on the simplified model. And we'll shortly talk about what happens, why it's not exactly proper. So according to this model, initially we have ID versus VDS, which are this kind of linear thing, and then they start saturating, and then they become flat. You have another one for a different VGS, and then you have another one for different VGS. And when it happens, the border between these two regions is where VDS, this is the line of VDS equals VGS minus VT. So to the right of this, you have pinch off, and to its left, you have the triode mode of operation. Again, according to the simplified model. So these are for different VGSs. Okay? So what happens, the basic rationale behind this behavior is that the channel length doesn't change a whole lot, and the voltage across it is constant. So to the first order, it should be constant. Of course, we'll see it's not exactly constant in a minute, and how we came up with it. So that's for the pinch-off. So we have two regions of operation, and the condition for pinch-off is that VDS is greater than VGS minus VT. That's the condition for the pinch-off. Now, in this derivation, let's go back to this derivation we have, even for the triode region. The way I wrote my equations, I made a simplifying assumption that you didn't catch. So let's go back and see if you can identify that simplifying assumption. It's here. I'll tell you which equation it is. It's just this, the first equation I wrote. It's technically speaking inaccurate. So what did I miss in that equation? Let me tell you one thing. One of these terms is not constant. VT. Why is it like constant? That's correct. So when I say it's not constant, I mean it's not constant versus location, versus x, versus position. Think about it. Think about body effect, right? For each one of these little transistors, so you see the depletion region, originally I said the depletion region looked like this, right? So if I had no VDS, I had a kind of uniform depletion region underneath. But if I apply larger VDS, which side would have a larger depletion region? This side, right? Because you have more negative voltage. So it becomes like this. It becomes oblique. So at different places underneath the channel, I have different widths of the depletion region. It's as if I have different source bulk voltage for these tiny transistors at different locations. Basically, I ignore the body effect for the individual transistors. Because each one of them sees a different source bulk voltage because it sees a different depletion width region underneath. And because of that, VT is also a function of x, really, in reality. And in fact, you can write expressions for that. And interestingly enough, you can actually solve the integrals. I mean, you can integrate them analytically. They look really ugly. And they give you an equation that's not like this. And they don't give you a kind of square law behavior, like the one you see here in the pinch-off region. They give you something else. But if you plot them and plot them next to the square law, if they're close enough. That's called the bulk charge theory. And if you're interested, I can give you some references on the calculations. You can go and look it up. And it's a kind of it's a more, it's a longer derivation, right? It's nothing fancy. It's basically essentially the same thing. Just you take the fact into account that VT is a function of x, and then you put that functionality in this integral, and then you integrate it. But the thing is, that's what bulk charge theory, and you can come up with expressions. So the point to take away from this is that even this expression and that expression are not correct, technically speaking. They are approximations. And even the bulk charge theory is not exactly correct, because we made certain assumptions to arrive at these. So layers of approximations upon layers of approximation. Now, why am I emphasizing this? That these are all approximations. Because when we go to design, I want you to realize that these are approximations. You don't get too hung up on, say, oh, why did you drop that term? So, well, it's small compared to these other terms, and these are approximate anyway, right? I want you to realize that even this is approximate, even that's approximate, even the bulk charge theory is approximate. Everything's an approximation. Right? You never kind of solve the grand unified theory for every kind of simple calculation you want to do, right? You know, or even kind of, you don't even go and solve the Dirac equation for everything you want to solve, because it's impossible, right? For all the electrons, you have to go and do that, and just come up with approximations that make it possible, make it track them. So, but anyway, so that's something to keep in mind. So we make a very distinct approximation here, and we assume that Vt is not a function of x to arrive at this result. And you can do it with that. You won't do it, it's just too long. Okay, any questions up to here? Alright. Okay, so if not, let's talk about several different things. Let me just see if I haven't missed anything here. Oh, actually, I have. That's one thing. Now, let's go back to this pinch-off behavior. So I said, well, I kind of hand-waved my way through it. Said, well, you know, at this point, the channel length doesn't change that much, and therefore, this current remains constant because the voltage across the channel. So if you look at this channel, so this was the MOSFET, N+, N+. Then you have this channel, and then this voltage is always VGS minus VT, which is always true. But then I said most of the voltage will drop across here, so if I increase or decrease this voltage, this will not change much. So it's like a transistor with the same current as it could have had before. But it does change somewhat. It's not that it remains zero. I mean, it changes, it don't remain zero. So if I apply a larger VDS, this point goes a little bit more to the left. And if I lower my VDS, this point goes to the right. And hence, effective channel length is changing, right? So what do I expect to happen if I apply a larger VDS? The effective channel length becomes smaller. What do I expect to happen to the current? The current dependent on inversely on L. So the shorter the channel length for a given VDS, I will have a larger current. So it shouldn't be that surprising to you if I tell you that these curves are actually slanted like this. Right? This is very similar to something we had in bipolar transistor, right? What is it similar to? Yeah, basic modulation, or the Ernie effect. This is actually called the channel length modulation. Right? So a change in the VDS affects the width of the channel length, and hence changes the current. So how do we model that? Well, they say the physical channel length, the way you, or something we call it drawn, because we used in the past, when we were to do the layout, actually it was done through lithography, and they were hand drawn. The negatives were hand drawn a long time ago. Right? The masks were hand drawn. And so you see the drawn L, which is actually kind of the physical L, is what? So the actual, well, it's whatever it is, but then the effective channel length, this length, is going to be L drawn minus XD, the width of this depletion region, right? The part that's depleted of charges. So you can say that. And then if you come back to this equation, we really have to modify this equation slightly. I can say, well, it's really mu n Cox over 2 W over L effective VGS minus VT squared. Right? And this L effective is not constant now, because I know this L effective is now a function of VDS. Why? Because this XT is a function of VDS. L drawn is not. So if that's the case, what can I say about the variations in the current versus VDS? So I know this is a function of VDS. So dID dVDS is going to be what? Well, these other terms are not a function of VDS. The only term that's a function of VDS is this term. Right? So let's differentiate it. We differentiate all these constant terms are out, W. So what is the derivative of 1 over x? Minus 1 over x squared, right? X to the minus 1 is minus x, minus 1, x minus 2. So it's L effective squared, and then the derivative of L effective. So at VGS minus VT doesn't depend on VDS, and then I have to calculate the derivative of this with respect to that. So it's D, or I can actually write it as DL effective dVDS. Right? But what is it based on that expression? Well, it consists of two terms. This term is a constant, and this term. So it's really nothing but minus dxd dVDS. And that minus sign cancels this minus sign. Okay, so I get rid of that. So what is this? Let me just use a different color. What is this? I captured this square, so I captured one of the L's. Okay? So it's like writing it as L effective times L effective, I captured one. Then I take it out and just. So, what is it? What is this thing inside this ugly looking purple balloon? ID, right? That's the ID itself. So I can rewrite this as ID over L effective times dxd dVDS. Okay, fine. Now, what I need to calculate, you remember before I defined something like when I was talking about the bipolar transistor, I said the early voltage, which was kind of the intercept point of all of these things, this is minus VA, was a point, VA, was the ratio of ID to the derivative of ID with respect to VDS. Right? Because we saw the larger the current, the larger the variations. Because the percentage of the variation, the fractional amount of variation is fixed. If you double the current, it's the same change in VDS results in the same fractional change in the current, which is twice as large in absolute terms. So this should be a constant quantity. So you can define a similar thing for MOSFETs, actually defined as 1 over lambda of L. And it's basically ID over dID dVDS, or you can even define an early voltage if you want. And from this expression, it's very easy to calculate. So it's basically this guy divided by that, so whatever is left will be there. So it's L effective times over dxd dVDS, which is often written as L effective times dxd dVDS to the minus 1. So this is your so-called VA, the early voltage if you want to define it by definition. And of course, you want a larger VA because the farther out this point is, the flatter these lines are, the closer to the kind of flat. Because we'll see, you want this to be as flat as possible because you want to have independence between the controlling terminal and the controlled terminal. And you'll see how that limits your maximum gain in a transistor. This is basically what limits the maximum achievable gain from a transistor. The flatter these lines are, the higher that gain is. We'll do that calculation later. Okay, but now, this is something interesting. What does it tell you? So if I were to increase this VA, what can I do? Well, this depends on the properties of the depletion region and the doping concentration and all those things. I can't do much about that. I mean, it's whatever it is for a given process technology. Right? But there is something here I can play with. L. What happens if I make my L larger? Would it make it better or worse? Would it make this effect, this channel length modulation effect, better or worse? Or in other words, is that, in fact, what happens is that you have a larger channel. So the same change in the VDS, if the same change in VDS results in the same change in this length, this XD, the total fractional change in channel length is smaller, because now it's a smaller fraction of a larger channel length. So does that mean that we want to make the transistor channel length as large as possible? Well, the short answer is, well, it depends what you're trying to achieve. But what do you pay? What is the price you pay for this? There are always trade-offs, right? We'll see this very often if we go in the design and say, well, if you do this, this will affect this one, I'm going to improve this property and degrades that. So what does it degrade if I increase my channel length?
Current due to the...
Right. The current per voltage, right? In other words, my transconductance. We'll calculate that in a second, but it affects my because if I make my L very large, this whole thing, I may get a very puny amount of current, a very tiny amount of current for a given change. So I can't induce a large change in the current. Basically, my gain is affected by that. And we'll do later on a calculation which shows what is the optimum for all these for a given transistor, taking both of these effects into account. But one good thing to remember is that you have, unlike the bipolar transistor, in a MOSFET, you actually have control over this. Because MOSFET is done as a lateral device, as a surface device. So you control both the W and the L of the transistor. In a bipolar transistor, you usually only control the emitter area. Right? You can't control the base width, because the base, as you will see, we'll discuss this later, the way it's built, it's usually done as a vertical device. So it's done in the bulk of the transistor. But here, this is done on the surface. So if I want to make one of my transistors larger, I have to make one transistor have a larger channel length. So I have 2 degrees of freedom I can play with in a MOSFET. So I have more versatility in that sense. And if there's one transistor in which I need a large output resistance or large VA, I can make L large in that transistor. Okay, so that's for that. Any questions on this? Now, the other thing is that now we have a couple of regions of operation defined, right? So let's go over the different regions of operation and see if we can actually capture all different modes of operation the same way we did for a bipolar transistor. So now we have 2 primary controls of the transistor. Well, we have really 3. We have the VGS, the gate voltage, the drain voltage, and the bulk voltage. But let's say we don't worry about the bulk voltage for now. And worry about the gate generators, so VGS and VDS. Right? Now, if VGS is greater than, or let's say there are 2 modes. It's smaller than VT and greater than VT. If VGS is smaller than VT, what can I say about the transistor? It's off, the first order, right? So for our purposes, we'll say it's off, but what we really know is that it could be sub-threshold. We'll talk about sub-threshold next time, a little bit. But so it could be, there could be some, so off basically in this sense means that there's no current flow, because based on the simplified model, based on strong inversion, there is no channel charge. But now there is a little bit of channel charge, we know, even before we get to that point. So there could be sub-threshold current. Okay? Now, if VGS is greater than 0, it means that we have a channel length. But then now we have to look at the relationship between the VGS and the VDS, right? So if VGS, well, let's say if VDS is small, more accurately, smaller than VGS minus VT, then we are in what region? We have the channel extended all the way from the source to the drain. We have the pinch, we have the triode region, right? The region we derived first. And then we have that expression for triode, this expression. Right? And then we have, if it is greater, VDS is large enough, then we can pinch off, we can have a pinch off, we are in a pinch off region, and we have this expression. Now, the way this expression needs to be modified, one simple way, again as an approximation, to modify it is to modify it in the same way that we modified the bipolar transistor. in that Taylor series expansion. Okay. Now, one quick comment about the nomenclature. I don't know who came up with this terminology, but it's really as bad as it could be. Now, I'll tell you what. So this terminology is okay, but there are other names for these regions. This region is sometimes called saturation. I can see why they talk about saturation, because the current is going to be saturated. But unfortunately, we have also saturation in bipolar transistors, right? Do you remember the bipolar transistor curves? We have this in IC versus VCE curves. We had, this was the saturation region, right? But now this corresponds to the triode, which also is called linear, where it's not, and also ohmic, where it's not exactly either. So that's why I try to use these terms, which are the least confusing of them. So, and I suggest you use those two. We use triode and pinch off, saturation and forward active region for bipolar. Triode and pinch off for MOSFETs. But so, if someone comes and says, well, yeah, the transistor is in saturation, you have to first question, what kind of transistor is it? MOSFET or bipolar? Because they mean kind of opposite things in those two contexts. Anyway, alright, so let me stop here, but then what we'll do next time is we'll talk about short channel effects. So we'll see what happens when we make the MOSFET smaller and smaller. First of all, let me ask you a quick question before we go. Why do you want to make the transistor smaller? Based on the expressions we have. Look at this expression. The speed of the transistor, how fast the electrons, how long does it take for electrons to get from one side to the other? Depends on L squared. So the shorter I make that channel length, I expect to get some improvement. And we'll see exactly what that improvement is. So to make the transistor faster, of course I have to make the distance that the electrons travel smaller. And that's why I want to make it smaller. But then when I make it smaller, some interesting things happen that go beyond our first order law. And then we'll talk about some of those. And then we'll talk a little bit about, the equivalent law. And the capacitances and all those things. In the transistor, and we'll talk a little bit about the subthreshold current. Any questions? Alright. Okay, well, I guess I'll see you on Friday, and your homework is